Okay, so this is the diagram that we started with, and we know that we have to backtrack one particular path now. So why is propagation that important? Because we are coming up with a gradient descent optimization to go ahead. So we have to know that, okay, what are the inputs? Like example, multiple times you need not calculate the values. Example here, okay. So since I know the value of these, I first backtrack this here, I got to know that. The next time I backtrack here, I got to know this value. Again, I backtrack here, I got to know the weights. Backtracking, I got to know the weights of this, okay. Now the second time when I have to find another path, I'll take another path because I have to keep updating the neuron. Suppose I have to update this particular neuron, okay. So I have to get to know the weights adjusted to this. Since I already know the value of this, I can just utilize this value and update the next. I need not again calculate it from the start. Okay. Example again from here, I have to backtrack it over here and come to this path. Okay. So I want to backtrack this path from here to here, from here to here back. So if I have to do that, the first thing that comes up to my mind is, see, I've already finished this path. I know it. And I've already, this path is also known to me. So only thing that I have to next update is only this path and this path. So I can take up all the other values from this and I can work ahead with these two. The similar, I already have this path. Now I just have to get from here to here, I'm traversing like this back. Okay. So if I have to traverse back like that, I already know 1 and 2 path is ready. The third path is here. Okay, this I will be calculating and this I will be calculating. So it is easy. So I already have the stored values. So I'll only retrieve those values and I'll start working on with that rather than recalculating it for the entire values. Okay. So we actually did the loss function, right? So L of theta divided by partial derivative of W was, what was it? Can you tell me? Partial derivative of L of theta divided by what?
Delta
Y
x.
cap.
Y cap into delta Y cap divided by delta. I want this.
H22.
Yes, I want this part. H22 into delta, sorry, H22 divided by
H21, ma'am.
I want this part.
H12.
H12 into delta H12 delta X. Okay. This is the broader picture of it, but each and everything, even this output layer will also have an activation and the pre-activation, because that has either a softmax function, you'll have a different activation functions that you might be applying onto it as well. Okay. So right now, what I have to do is I have to actually get to know, I'll go to the next below step of it. What do? I actually have, this is my loss function. From the loss function to this, I have this value. I'll go the next step of it. Okay. So what from here, what I do here is I have an activation function called as A3. Okay. So I will write this as A11 or A12, A1, A23 and A3. Okay. So there are activation functions that I've written for these and these. So it is A12, A23 because it's the second hidden layer. So I write it as A22. I'll write it as A22 and A3. Okay. So these values now, I have to trace it in such a way that it goes more simpler. So from L1 to delta Y, I have that value. So which will be equal to delta of L of theta divided by delta Y cap. This is my first easy step. My next easy step is, here itself I have so many calculations that I have to perform with one single neuron. So I'll split it up into another step. From AY to AY3, what is the operation that I have to perform? Into A Y cap divided by delta A3. Oh, sorry, A3. That's my the next step. Then from there, what I do, I get to know this operation. So I'll again split up that. So it's going to be delta A3 divided by delta H22 into. So again from this, okay, from H22, there's an operation with A22. So I'll split up this as delta. So I'll write this as delta H22 divided by delta A22. And from A22 to H22, delta A22 to H22 into, see from H12, sorry, H12. From H12, there's an operation that I have to perform to A12, delta H12 with delta A12 into delta A12 into delta X. Did you get to know how did I actually come up with the next step? Backpropagation. We have split the operations. The first operation is from here to here. The second operation within the neural network. Third here. Again, fourth operation. Fifth here. Again, the sixth operation. And finally, the seventh. So, when I perform this operation like this, I can immediately extract this value of it. So these are all the smaller steps to get my data accumulated in the matrix, or I will have my data being present. I can just utilize that data and go ahead. So I will start optimizing my weight updates. Are you clear about this? This is how you backtrack each and every neural network, whether it is a smaller, whether it is a multi-layer, or whether it is a huge complex neural network. Each and everything is being calculated and stored it for further use. It starts applying onto it. There are equations for that. We derive certain equations for that. So let's start deriving the equations for that. So are you clear about this? Let me go ahead next.
Yes, ma'am.
Okay. So I'll clear. Okay. Let me start writing it. So derivation of the backpropagation. I'll be indicating the similar things, okay, with small diagrams in between. So it will be helpful for our understanding. So we already know the weight is basically, when I consider the gradient descent, I'll have a minus sign. Do not forget that. It's with respect to the training error or the loss function with respect to the weight updates, right? This is what we perform. So we perform this delta Wji. So it's going to be Wji is equal to Wji plus delta Wji. This is our perceptron training rule with gradient descent and the delta rule applied onto it. So we know, till here we know what we are actually doing. It's very simple. We have already seen an example, but I've written a little mathematically. That's the only difference. It's the same thing, which is minus n. Delta theta w is basically OD, that's T minus of O into X. Okay, so a simple annotation that we have done, so not to worry much about it. Okay, so we already know this equation. So from here, I start applying onto it. So let me clear it again. So the simple thing here is, I have some notations where I'm going to write it over here. xji is equal to input. Input from where to where? Let me consider I have an input called as x. I have an input called j, that is I'm going to get an output called as oj. Okay. So here it basically performs the summation operation. So there will be an output neuron as well for this. So I will be performing a summation operation over here with respect to wji. This is j and this is the ith neuron and the jth output neuron, and the weight of this is going to be ji. Okay, so ji, and I still have multiple neurons here and here, but I'm not considering right now for that. I just only want one output neuron. So this is my output neuron, this is my input neuron, a representation that I'm doing for your easy understanding. So wij into xji will be my summation of this pre-activation function. So my activation function can be anything. It can use anything, any of the functions, and it performs, it will give me my output. Okay, this is my output value. So when I tell this, now I'm representing xij. I hope you get to know that it is the input that is being passed from xith neuron to the jth neuron. So I write it as xji. Okay, and the weights are again from the ith neuron to the j, we write it as wji. Okay, so these are the values. Now what I'm going to write it here is, I don't want to every time represent this summation. Okay, so I will represent this summation to be as net j. Net j is in the sense it is a complete value of it, summation value. So I'm writing it as net j. oj is the output, we are clear about it, and we have tj. Tj is the target value. Every input instance will have a target value associated with it. I'm going to write it as tj for that. Okay, so I have oj, I have tj, I have xji, sorry, which is my input. I have my weights, I have my summation function. So all of these terms are defined to us. Now I will start deriving the equation. How do I derive the equation? Just for this, an example only for this, how do I write the backpropagation now? So it's going to be delta ed divided by delta wji. I have to write the backpropagation for this, which is going to be equal to, how do I start writing it? So this is my loss function over here. How do I write it? Can I write something like this? The loss function with respect to net j. The loss function with respect to net j, and from net j can I write something like this? Can you correlate what are these terms? See, from the output I perform this, I get the error value. I already have that ready with me right now. So the output and the target is being taken into consideration. I got the training error. So basically what we do, we update the weight in the sense this training error is with respect to the weights, right? This is what we normally do. So with respect to that, when I'm performing, it's going to be ed by wji, which is equal to ed. I've already calculated this part. Okay, let me change the color for you. So I've already calculated this part, which is nothing but ed. So from ed with respect to, what should I do? Ed with respect to the pre-activation, which is nothing but summation of wji into xji, which is nothing but net j. So I'm going to write ed with net j. Okay, and the next into this net j, whatever the value that I got with respect to the weight, this part. I perform this. Finally, I will backpropagate it into the simple terms. You're able to get this difference. What are we trying to do it? The similar steps, we did it very simple with respect to the multi-layer neural network. I just showed you by writing their weights and all, but this is how it is actually represented mathematically with the partial derivatives. Are you able to correlate the previously discussed topic to this and get to know the difference what we are doing? Because this forms, I've already calculated OJ and TJ, which is nothing but my error difference. My loss function is already known. What is my loss function? TD minus of OD, the whole square. My loss function that I did, mean square error divided by 2 for each and every instances. So this is ready now. I've got this value. So now when I get this value, basically I got the error value of it, but on what it is basically going to be dependent on the summation, because the input of it, the output error if I get, there should be some input to that, which is nothing but all the inputs that has been passing for the neuron. For this neuron, it is going to be delta net j. Now from here, I've calculated this part. So now this part is over. From here, I have to again go back to calculate the ith value of it. But the main constraint here is it's going to be dependent on our wji. So I'm going to write net ji into wji will actually give me my value. So this particular term, okay, whatever I get this, I will write this directly as xji. Because I've already got the summation part of this. This part is ready, and the weight update, when I apply this, obviously I'll get this value. So I'll be writing directly like this, called as net delta ed divided by delta net j into xji. So this is basically what it actually means by looking at this diagram. And I've explained to you. Let me know if you have any doubts over here. I can again revise. Nothing? Can we go ahead?
Yes, ma'am.
If you really have any doubts over here, you can again re-ask me. It's not an issue. It was the same type that we did in the previous. We had all the neural network model, right? We backpropagated it. How did I get my ED error? It is with respect to the output called as y cap. Okay, so this was the output. So output target minus of the output, the whole square into 1 by 2 basically gives my ED value. So I have already finished this part. So this part is over. Okay, so when that part is over, what was else remaining over there? Because this is my output, I just had only one single neuron. You omit this part for now. I just had only one single neuron called as X. Okay, I still have the activation function. Till here it is over. So till here it is finished. I've calculated that. I got the output of it. So from the output of it, I had the target value. I calculated it. I got ED value. So now ED value is ready. But before that, I have to get to know what is my other calculations that I have to do. So I just had one input neuron called as ji. So this was my ith value, and this was my j value. There was a wji for it. So for this, when I have to mathematically derive something, which means that this pre-activation was given by something called as net j. So what I do from here to here, I perform the operation which is called as delta ed divided by delta net j. Simple terms. Now what I did again, I have to calculate this part to backtrack it. So to calculate that part to backtrack it, it's basically again delta net j divided by delta wji, because I have the weight to calculate over here, which is nothing but when I get these two, I will directly write it as xij, because xij itself is going to impact onto this net j. So when I have this value, I can easily get the other value. So this term I will write it as delta ED divided by delta net J into xji, a simple term. Okay, so this is how I get it when I have only single something like this. Very simple. One input neuron, direct output neuron. There are certain summations that we perform. But now if I have some hidden layers coming into picture, so what are we actually going to do with that? Okay, so now we'll go in detail step by step. What do we perform for that? Case 1. What is the training rule of output unit weights? What is the training rule? Case 1 is, what is the training rule, or I'm going to identify the training rule for output neurons. So when I tell output neurons, what is the value that I will get? Now, this is completely mathematical. You have to think with respect to coding perspective. Coding perspective in the sense, consider that we are working on a program. So the program is like this. I have multiple layers. I have an output neuron, okay, which is all connected. You can consider it is all connected. Okay, something like this. So now first I have to consider this output part. I have to calculate for the output part. So how do I do? So I will write it very neatly what my diagram states. This is my output neuron. From my output neuron, I will be calculating ED, which is my loss function, L of theta. Okay, so this I will be writing it something like, from here I will get the output called as OJ. OJ is my output, and I have a summation function for this called as net J. Okay, this simple term that we see above over here, this part, I've written it like this with the actual terms ED, net J, OJ, and that is L of theta. So now I have all the values. Now if I have to backtrack this, or if I have to get a value for this, what will I actually be doing? Delta of ED divided by delta WJI. This is my complete path that I'm going to track for. Okay, so okay, right now I'll be using only delta net J because I'll be working only with these two. So I will write it as net J. Delta ED divided by net J from here to here. Only from here to here, what will be the operations that I perform? Which is delta ED, the partial derivative of ED with respect to OJ, because I'm worried about the output here. Okay, so that is with respect to the output into delta OJ divided by delta net J. So this to this I want, from this to this I want, two operations. So the two operations I've written over here, and we already know delta ED with respect to delta OJ is basically 1/2 summation of something, okay, into T minus of O the whole square. Because this is what a loss function is, and I already know this value, so I can substitute that value in this. Okay, so I'll start working on with that. I have to get a partial derivative of this. The partial derivative of this I have to perform on this, so which is equal to 1/2. I keep the summation as it is. When I do a partial derivative of x square is equal to 2x into delta x. We already know that. So I'm going to write it as 2 into T minus of O, that is Tk minus of OK, because output normally it is represented with K. Okay, so, or I'll write it as J because here I've taken it as J, the Jth value. So Tk and Oj, okay, into delta of x. I have to write delta of x here. Delta of x is nothing but T minus of O, Tj minus of Oj. This two gets cancelled. Okay, I'll be getting Tj minus of Oj into, whenever I perform the partial derivative, it's going to be delta of Oj. Because I'm performing with Oj, I'm going to write it as delta of Oj, which means that Tj minus of Oj divided by delta Oj is my term that I have right now. This term here, Tj, is neither independent of Oj. So I can, it's not dependent, so I'll eliminate it. Okay, but the partial derivative of, so it's basically delta of x divided by delta x is basically 1. One second. So delta of x divided by delta x basically is 1. Okay, but I have a minus sign over here. Okay, I have a minus sign over here, so I will be taking it as minus of Tj minus of Oj. So I got to know the first term. I'm ready with my first term because I know the loss function with respect to the output is basically the mean square error, and I apply the partial derivative of it and I got a value of it. So my first term is ready. But what does my second term do? What does my second term do? My second term is with respect to delta Oj divided by delta J. That is, there is something that is happening in between the activation function and the pre-activation function here. So this is my activation function, my pre-activation function. So when I have to split up that, I will be writing the main performing operation over here will be that, suppose I take, for the activation function, I take a sigma function on it. Remember, if I take a single perceptron, we used signum. We used a signum function in the previous class when we took an example with perceptrons. So I performed a signum function. So I'll consider here I'm going to use a sigmoid function over here. Okay, suppose this is an example. So I have a sigmoid function as my pre-activation function. So I'll be writing this term, this term as delta, okay, with respect to sigma of, on what am I applying this sigma? On what values am I applying this sigmoid function? Please do recall on what am I applying this sigmoid function. If you remember, SGN output is equal to SGN of something. What is that something? Don't you remember that?
Weights into input.
Exactly. So weights into input. What is weights into input here? What are weights into input here? Net J.
Yes, ma'am.
Because net J is what? Summation of weights into X, right? So I can write it as net J. So it is sigma of net J divided by